Hi, I'm Jeff Irwin, and happy to be doing this talk on Channel 9 for Azure Storage. Welcome to the talk. We're going to be talking about storage performance, scalability, and security. So in this talk, we're going to be covering just a brief overview of storage. Those of you looking for an introduction to storage, I strongly encourage you to check out Jason Hogg's talk that'll be actually at Build. Check that out. It'll give you a full overview of our service, what it can do, the different data types. Those of you who are more familiar with the storage service, already using it, familiar with it, definitely check out this talk. Follow along. This hopefully will be productive for you. We'll also talk about storage internals, so you understand design principles and architecture choices that you can make. And then we'll go into just some quick 5-minute fixes that you can make to your code that should markedly improve performance, including one set where we'll take a code sample and improve its performance by about 99%. So definitely stick around for that. And then finally, we'll also be talking about some security considerations. We've had a lot of developers asking us lately about security considerations for Azure Storage, so we wanted to make sure we take a few minutes to go into that. So to start off with, just a few minutes as a reminder about Azure Storage. We have, it's durable cloud storage, really, and it comes in a few different flavors, but that's really our goal, is storing all your data with high durability in the cloud, accessible from anywhere. We do 3 strongly consistent copies in one region, plus optionally with geo-redundant storage. You can have 3 more copies geo-replicated to another region for even more durable storage. It's really high scale. At the moment, we're currently serving millions of transactions every second, and we already have trillions of objects stored. So we're at a very high scale. Many of the largest Microsoft services are using Azure Storage already. So that should give you some idea of just how scale we can operate at and how you can use this in your applications. And then finally, flexible. We use REST APIs for all interaction with the storage platform. It means you can use it from any platform. You can use it from any platform you want that's part of your application. We have fully supported libraries in .NET, Windows Phone, Windows Runtime, Android, Java, C++, Node.js, coming more all the time. We're explicitly making sure that the C++ and Java libraries work on both Windows and Linux. So we really want to embrace whatever platform works for your application so that you don't have to do anything unnatural to use storage. And if we don't have a particular language you need, as we said, they're just REST APIs. You can always write directly against those. Storage types. Azure Storage is a really flexible platform. First type we support is called blobs. There's really 2 types of these. There's block blobs and page blobs. The block blobs are for just ordinary content. They're, any photos or documents, logs, files, anything that you would normally read and write all at one time or in ranges is well suited for block blobs. Then we have page blobs. Most common scenario for page blobs is going to be disks. So anybody who's using Azure disks, that's all page blob data underneath. You can also use it in a few other scenarios for random read-write, particularly if you're doing random writes. You may want to explore page blobs. Next up, we have files. This supports the SMB protocol from the cloud, so you can access it just like a file share. The one interesting characteristic, as opposed to disks, is you can access it from many VMs at a time. Whereas a disk can only be mounted by a single VM. So if you have data that you need to share among multiple VMs in Azure Compute, you can use the Azure Files service. Then we have tables. This is a NoSQL store, most frequently used as a key value lookup. That one's for structured data. It's, row-like data, but schemaless. You don't have to have the same schema for every row. That we'll be digging into quite a bit today. And then finally we have queues, which is for durable messaging. This is for handing off messages between components of your application and making sure that those messages are never lost, they can be resumed, and that message always gets fully processed. Next, we're going to talk about storage internals. So why are we starting with internals first? We really find that developers who understand the internals can make much better design choices. Once you understand how the platform works underneath, we find that it's much easier to figure out how should I design my application on top of it. So we're going to spend a lot of time on that. The one nice thing about this is because all of those different data types are hosted on the same platform, any of these principles will work for any of those data types. So understanding the internals will help you make design choices for blobs, tables, queues, any of the different data types that are all hosted on the same common platform. So the Azure storage architecture really is 3 tiers. So the first tier of the Azure storage architecture is the front-end tier. This is a stateless layer. It's really meant for request handling. So it handles all the request validation. It'll do metering, throttling, auth. All those things are handled at the front-end layer, but it's fully stateless. So any request you send to the storage service could go into any one of the front ends. Beneath that, we have what's called the partition layer. This is what really serves the request. This is what does all the heavy lifting of processing the request, determining what data it's for, and then fetching that data from the data layer. The existence of this layer is what enables strong consistency and batch transactions. We'll be spending a lot of time on this today. And then finally, we have the stream layer. The stream layer stores multiple replicas of your data, again, keeps it durable, and really doesn't know anything about that data logically. All it does is store the data and make sure that it's kept durable. So Azure Storage Partitions, just to start there, they're really the most important concept in designing your data. A single partition is served by a single partition server. So it ends up being the scalability limit. And then a single partition server can serve multiple partitions. The scale of a partition can't exceed what a single partition server can handle. So it's really important when designing your data that you allow your data to spread across partitions. The 2 kind of design considerations that are kept in tension here is that data in a single partition can be updated atomically. That is, it supports batch transactions and other atomic operations. Data in separate partitions can be load balanced across different partition servers. So you want to allow for that as much as possible. There is no limit on the number of partitions you can have. So as you start specifying partition keys, there's no need to try and keep the number of partitions low. You can use as many as you want. For references, the partitions are specified differently for each of the data types. For blobs, the full blob path, including the blob name, is the partition key. Essentially, each blob is its own partition. For tables, the table entities each have a partition key that you specify. You may have multiple entities within a single partition key, but all of those will always be served by the same partition server. Then queues, the queue name is the partition key. So all messages in a single queue will be served by the same partition server. And then for files, a single file share is a partition key. So let's do some examples, just walking through our 3-tier architecture and see how these requests get processed. These examples are all going to be based on the table service, just in terms of what they logically look at. But you could imagine this working well for blobs or queues or files as well. So in this first example, we just have a single object, a single request for a single object, and it's been fully specified. The request is specified partition F and row 102. This happens to come into front end number 2. It could have gone to any of the front ends. Partition server 3 is hosting partitions F through J right now. And so the request is going to get routed to partition 3 based on it being for partition F. Then partition server 3 finds out the data is actually hosted on stream server 2, and so it's going to route the data to stream server 2. These are very fast and efficient requests. Let's look at a second request. This one's also for partition F, but for a different piece of data. And so you can see the request flow goes through a different FE, but again, the same partition server. And this is really important. This is going to the same partition server as the previous request because, again, it's for the same partition, partition F. And then finally, it just goes to another stream server. The data can be spread all across the stream layer. And then this is for another request. Again, simple request, single object in a partition, just goes to a different partition server. You can see this one's for partition T, which goes to partition server 4. The data happens to be on the same stream layer server that we used in the first request, but that's mere coincidence. And then finally, this is just an example of what we would call a batch request. This is a request that asks for 2 pieces of data. It's in partition W. We get down to partition server 5 that's serving that partition. But because it needs 2 pieces of data, it ends up having to go to 2 stream servers. This is a little less efficient because we need multiple objects from multiple servers. So overall, the key takeaway here is Azure Storage is going to be most efficient for single object operations. Single partition operations are going to be much more efficient than multi-partition operations. We'll look at a multi-partition operation in a minute to show why. Let's talk about designing your data. So just to remind everybody about table server structure, this is just a sample table here. We've used the user ID as the partition key. Just as an aside, user ID is a great partition key. There's no need to use a first 2 characters or anything like that. You can just use the user ID, maybe a GUID or a hash of the user ID if you want to make it random. That works as a great partition key even if you have millions of them. Next we have row keys. That's going to be specifically identifying an identity within a partition. And then finally, with each entity, we have a set of properties. Again, table storage is schemaless. You can have any set of properties associated with each entity. They don't have to follow all the same schema. So just to walk through the table structure, again, this is the kind of key points here. You've got entities with the same partition key are always served by the same server. So all these with user ID 1 are going to be served by the same partition server. User ID 2 may be served by the same partition server. It could be served by another one. Then we talked about row keys. And entities have properties, but they can be completely different across different entities. So let's talk about 3 different query scenarios. We look at a US cities table for an example here. So this is a table of just some cities in the states of Washington. So we've used state as the partition key, and then city as the row key, and then just as an example property, we've put the population of each city into the property values. So as we talked about before, this is very similar to what we looked at earlier. We're looking at the US cities table. Partition key is Washington. Row key is Seattle. We're going to end up over on partition server 5 because Washington starts with a W, and then going back to stream server 2 for that object. This is really efficient. It's one object from one partition. This is really what storage is designed to do. It's very fast and very efficient as you work through this. Here's the second scenario. Second scenario here, you have a partition scan. So in a partition scan, you see that we've specified a specific partition key, Washington still. So we're only involving one partition. But now we've just put a filter on population, just said all cities with more than 10,000 people. This is still going to be a little less efficient. As you see, we've involved now 2 data servers. We're going to have to scan a lot more entities in order to be able to respond with the data. And then finally, we have table scans. These are by far the least efficient operations in storage because these span partitions. This is similar if you were using the blob service to doing a list blobs operation or queues, doing list queues. You're going to be spanning partitions to do those operations. And what you see is this kind of fan out as we're using multiple partition servers, multiple stream servers in order to get all the US cities with more than 10,000 people. These are really efficient. We want to avoid them anytime we can in our applications. What's the cost of scans? So the first one for your application, they're going to be slower. What you see is that they're inefficient and they're going to take much longer than point queries. One of the reasons for that is when you look at the scalability limits, table storage can handle 20,000 entities per second, but that's based on the number of entities scanned and written. A request that scans 1,000 entities to return one counts as 1,000, not one. So you can see how you can quickly pile up the number of entities scanned and get to that scalability target actually very quickly. What happens when you exceed that scalability target? You'll find that your storage account starts to get throttled. Another piece here is when you see this 1,000 to 1 ratio, all that time scanning is time not spent returning data, which means this is just going to have a negative impact on the performance of your application. So how do we avoid them? So we're going to look at an example right now of how to turn a table scan into a partition scan. This will make a pretty big improvement in an application. So to turn table scans into partition scans or partition scans into point queries, we use denormalization. This is a word that if you're coming from a SQL background, probably is not something you've been encouraged to do over the years. But in table storage, it's actually a really beneficial approach. Denormalized data allows you to query efficiently, get exactly the data that you need. And unlike relational databases, table storage is very cheap. And you see the price there. It ends up being really cheap to store lots of data. So duplicating data doesn't have the cost that maybe it did in other databases. So again, back to our US cities sample. The partition key here was state name, and queries across states require table scans. So when I wanted to do a query for all the cities that have more than 100,000 people or more than 10,000 people, I had to include multiple partition servers to complete that operation. That's going to be just very inefficient. And also what you see here is we will have scanned many, many, many entities, but only returned a few. So just the density of results that was returned was very low. So now, if we try and improve this table, we keep all the entities that we had before because we may want to perform queries where we say, get me the population of Seattle, Washington, and that's a nice fast point query. So we kept that, but now we've added additional partition keys, which are population ranges. So you see we have a partition that covers cities that are 10,000 to 100,000 and cities that are 100,000 to 1 million. And then we've put the row key as the state name and city name. So now when we want to do a scan for all the cities that are within a particular partition or within a particular population range, now we can get that all from one partition. And then this is what you end up for exactly the same query we were doing earlier. You now see that we only have to involve one partition server instead of 3 like we did before. This is still a partition scan, so it's still going to have to hit multiple data servers, multiple stream servers, but we've made it much, much more efficient than it was before. So what you see is we've avoided scans by doing denormalization. You can use exactly the same principle if you have a lot of partition scans. You can refactor your data to enable point queries. And the cost effectiveness of table storage is really what allows this to work. Again, you can apply this to blobs. For example, if you were doing list operations because you're constantly looking for a blob based on one particular attribute, you may consider duplicating that blob with that attribute in the name so that you can find it much more quickly. Now we're going to talk a little bit about query first design. You saw an example of this in the previous, in the US cities that we walked through. But really, this is the core of how we design our data for Azure storage. What it means is start by determining what queries you will perform. Again, if you're coming from a relational database background, you may be more familiar with starting with what you're storing, starting with the objects and designing your data around that. In Azure storage, you really want to start more from the queries of saying, what will I want to know or what will I want to do? And then model the data for that. In the previous example, we knew there were two potentially common queries, so we denormalized the data to make both of them more efficient. So for example, we're going to look at a sample here, maybe from an e-commerce application. The example here is if we have customer orders with a retention policy. So we think about customer orders, one of the things that's going to happen a lot is somebody's going to want to be able to look up by a specific customer, by a particular order ID, getting the data about those customer transactions, customer orders. You may also want to get the whole list of orders that were performed by a particular customer, but that's much more rare that a customer is going to want their whole history. So we don't need to optimize for that as heavily. And then finally, there's an additional requirement here, which is for privacy and security reasons. We've said every transaction or order from the customer needs to be deleted. The record of it needs to be deleted after 6 months. We can't hold on to it longer than that. So we need to make sure that our tables actually enable that scenario fairly well. So the first try here is, again, what you might do coming from a relational database. You have a partition key here from user ID. That's good. Then we add in a row key. That's the order ID within that user ID. And then some metadata about that order. This table is great for finding all the orders for a particular user, but we don't do that very often. It's also good for finding a specific order by a specific user ID. But one thing that this table won't be good for is finding all the orders to delete. So if you imagine that every day I want to find everything that's more than 6 months old, the only way to do that is to scan the entire table and find anything that has a partition key or a date older than 6 months. This set of tables improves on that. So what we've done here is now we've said, because I have this retention policy that's really important to me, and I'm going to be doing it all the time, what I'm going to do is I'm actually going to split out my orders by month. You could use a different time range. You could use a day or a week, depending on your application needs. But we've split out the tables so that each of them captures orders from a particular time range. That way, as soon as that table is more than 6 months old, you can simply delete the entire table, which is only one operation. Finding all the orders for a particular user, you're going to have to query multiple tables now, maybe 6 if you're using 1 per month. But we already said that that operation is quite rare compared to the retention policy. And even that would just be 6 partition scans, no table scans involved in this. So this is going to be much more efficient based on the queries that we have. Again, you could imagine a different application with different queries and it would have different needs. And we might design the tables differently for that. But by starting with what we need to know and designing the data for that, we've ended up with some tables that are really going to make our application performant and not run into the scalability targets like we would have with the first try. Next one we'll look at is hot partitions. This can happen in blob storage, it can happen in queue storage, it can happen in table storage, it can happen in any of these, and really gets to how do you efficiently structure your data. So what is a hot partition? It's one partition in your storage account that's taking much more of the load than any other partition. So you have a single blob that's really commonly accessed, or a single partition key that's really commonly accessed. What ends up happening, as we've talked about before, is it presents a scale limit because we can't split it across multiple partition servers. So it can't be load balanced, which means you'll hit the throttling limits much earlier than you'd like to. So we want to avoid those wherever possible. So this is just kind of an illustration very quickly in terms of how this ends up working. we say partitions start off well balanced. We've got 500 transactions per second happening across all the partition servers. Then we say, well, what if partition server D and E start getting more traffic? Now there's an imbalance. Azure Storage is a self-load balancing platform, so it'll go ahead and actually automatically split out partition servers 2 and 3. It'll maybe move partition E to a different partition server to cool things down and get them back out more balanced. But what you see here is that partition D can't be load balanced anymore. It's now stuck. There's no ability to split things out. So it's doing 1,000 TPS on that server, and it may be able to increase a little bit more, but at some point it's going to run into the limit of what that server can do. And at that point you'll get throttling and other effects. So an example of hot partitions we see is logging. So let's look at that. When you're logging from multiple servers, something people would do all the time is that they would use a partition key that's just the day's date. It feels natural. It was my first try when I did logging was to just put in today's date as the partition key. The timestamp ends up being the row key and then some properties. The problem with this is the vast majority of inserts, in fact all of your inserts, will always be hitting one partition. And my experience in a lot of logging situations, insert is by far the most common action. Read is far less common, which means the vast majority of operations against this table are going to be against a single partition key, which means that'll work right up until the moment that you have too many servers, too many events, and all of a sudden you'll be hitting that single partition server limit. So what we've done here is we've improved this by giving each server its own partition. So maybe I have 18 servers or more, and I'll have each server writing to its own partition. This one represents a little bit of a drawback in that in order to find an event, I may have to do multiple partition scans. But again, we've said reading is much more rare than inserting data, and this allows each of the servers to be writing to its own partition to avoid hitting any sort of partition key scalability limit. The last thing that you might consider doing with logging is actually to not use tables at all, to use blobs. So if you use blobs, what you find is log data can frequently be written in batches. You can batch it up for a few minutes and then write it out to blobs. And then have each of your servers doing this. And then also logs are frequently read in ranges. You may want to retrieve all the logs for a particular hour, for a particular 5 minutes. So what we've done here is done exactly the same thing, but now we're using a blob container and time range for each of the ranges of time for a container. So in summary, when we're looking at designing our data across all the different servers, you want to choose a great partition key. That can be the blob path, the table keys, queue name. It really matters for all the data types because partitions end up being the limiting scalability factor. As long as you spread your data across partitions, you're going to get great scalability out of Azure Storage. As I said before, a table or blob storage, any of these can have millions of partition keys. So don't be afraid to use user IDs, GUIDs, anything like that as your partition key. It allows for really even load balancing. Denormalization is a great way to, again, improve your query efficiency by duplicating the data, making it easier to find the right table entity or right blob. And then finally, use the right abstraction. Sometimes blobs are a great solution even though it's structured data. Sometimes you may want to use tables or files. Use the right abstraction for your data. In general, blobs are going to be great for data that's written in batches or read in ranges. And then tables are going to be great for data that's a key value lookup. So now we've talked about kind of the internals and specific queries and query patterns that you can do. Now we're going to talk a little bit more about designing your application and some patterns that we see that can really help your application do well, either by using storage or using storage more efficiently. So the first one we'll talk about, this is one that a lot of applications are actually doing, which is just using queues to distribute work to a back-end role. So in this example, we've used a queue. A front end takes in a request for maybe some long-running process. That front end, instead of doing that long-running process itself and blocking out CPU resources on that front end, it's going to put that message in a queue, let the back-end workers handle it, and maybe store the results back into Azure storage. This allows for asynchronous processing, more responsive front ends, and then also, very importantly, independent scaling. You could have 2 front ends while you have 1,000 back ends, or any ratio you need to make sure that you're getting the performance that you want to have. Another thing that we've seen a lot of people doing recently is simple change notifications. So sometimes you'll say, I need to know when a blob changed. Or when an entity changed. And so you'll start listing the blobs repeatedly or scanning a table repeatedly. But as we've already talked about, those lists and scans, those are table scans, and they're not going to be very efficient. So instead of doing that, you can see a process here for implementing a very simple change notification pattern. So basically you have the client making the change. Prior to making that change, put a queue message in one of your queues that describes that change. What object, what changed, was it deleted, was it created, and specifies that. Then the client making the change makes the change. So it does the queue message first so that we make sure that the client didn't crash right after making the change. We want to make sure that the change was captured. And then an observer watches for the change. It pulls the queue regularly instead of listing blobs or tables. Pulling queues is very, very efficient. When it gets a message, checks to see if the expected change happened. If it did, it processes it. If not, it can let the queue message go back to the queue. Those of you familiar with queues, that's a kind of core concept of using Azure queues. And then you can let it go back to the queue and then try again later on the same message. Queue messages have a dequeue count, so you can see when the message has been dequeued maybe 3 times. Once that's happened, maybe you can assume that the client that was trying to make the change actually failed after it updated the queue message. And then you can just throw away the queue message and assume that the change was unsuccessful. One important thing here, as I said, you really need to make sure that the queue message was created before the change is made. Otherwise, you could lose the fact that the change was made and not perform whatever processing you meant to. Using shared access signatures, which we're going to talk about more in a minute, and cross-origin resource sharing, you can now actually make direct data access calls from your client devices. So it used to be that you would have to proxy all Azure storage data through your front-end web roles. That would mean you'd need more front-end web roles. You'd need to be thinking about scalability just as much as the storage platform needs to. And now we have shared access signatures, which allow for delegated access, and cross-origin resource sharing headers, which help with browser security features, to allow the device to just get minimal amounts of data from the front end and then turn around and send requests for additional data to Azure Storage directly, not requiring your front end to scale nearly as much. Also, let's talk about disks. So with disks, your scalability targets are very important here. You have 500 IOPS per disk, 20,000 IOPS per account, which means you can't have more than 40 disks per account. So if you're going to have more than 40 disks, definitely spread those across storage accounts. You can have up to 100 storage accounts per subscription. Avoiding the per disk scalability target, best practice for that is striping disks. You can use storage spaces to ensure that even load distribution, and you can stripe up to 8 disks easily. Even using PowerShell, you can go even more than that. So definitely stripe disks if you're going to be going anywhere beyond that 500 IOPS to make sure that you get good performance. We also have premium disks now generally available, ready for your use. Gets you higher IOPS per disk, and then additionally in addition to the higher IOPS per disk, also higher throughput. So you see the smallest disk, a P10, has 500 IOPS per disk, 100 megabytes per second, all the way up to a P30, has a terabyte of data, 5,000 IOPS, and 200 megabytes per second. So much higher limits than were available on standard storage. This is all SSD backed, so you're also going to get much lower latency, much more consistent latency than you maybe got with standard disk. So same best practices. It's all built on a similar platform, so same best practices apply. Stripe for more IOPS. One note here is to make sure you're using the appropriate VM size. For example, a DS1 can only do 3,200 IOPS, so you probably wouldn't want to pair that with a P30 that can do 5,000. You should use at least a DS2 to make sure that you can get all the IOPS you're looking for. So what we're going to look at right now is about 10 5-minute fixes. Each of these are really simple for you to go and add to your code today, and each of them should make a really big difference in your application's performance. So starting off with a couple that are useful for all the different data types. The first one's going to be using read from secondary. This is usually not thought of as a performance fix. This is usually thought of as an availability or durability change. But from your user's perspective, if they're requesting data from your service and you're trying that request on the primary, and the primary for some reason is temporarily unavailable, you can immediately fail back to the secondary to get that data immediately for the user, improving their perceived latency actually quite a bit. Couple notes on this. One, it only takes just even half of a line of code adding in this location mode for retries, and that's supported across, again, all the data types, blobs, tables, queues, files. But one note here, just remember the secondary copy is eventually consistent, so if it's a very recent write, it may not be reflected yet. One other one we see, I've made this mistake, and we've seen it a number of times. Make sure that this line, create if not exists, is not in your mainline code repeatedly. This line of code always makes at least one server call, and usually isn't necessary once you've created your applications tables. So typically you'll want to pull those out, create all your tables up front, and then let your mainline code just focus on the operation it's performing, not making sure that the table exists. With queues, you can use update message. Update message allows you to do a couple of different things. What this is once I've retrieved a message, in queues you have two-phase delete. You retrieve and then you delete the message. So once you retrieve the message, you can call back and update that message. You can update both the least time that you have, the invisibility time, to give yourself more time to process the message, and you can update the contents of that message. So in this case, what we've done is we've said both I want to update the invisibility timeout to give myself more time, and I've updated the content to say I'm done with some step one. What this allows is if my worker were to fail, then I can resume on the next worker from step one. I don't have to start over all the way from the beginning again. So this is a really good way to make sure that your application can be much more responsive. It doesn't have to re-perform a lot of work that it was doing earlier or that had already been done. And also allows you to use much shorter invisibility timeouts. You don't have to make sure that it's the longest possible amount of time that a process could take because you can kind of renew that lease regularly and allow another worker to get started more quickly in the event that your worker fails. For copying blobs, we support async server-side copy blob. This really helps your application scale. If you're trying to copy a lot of data, you can actually just call copy blob on our service, and then the storage service will actually copy that data for you. You don't have to be able to handle that from within your clients or virtual machines. This should really improve your scale, save you a lot of bandwidth. There's also a flip side of this one, which is there is no guarantee provided on the amount of copy time. Usually it's fast, but it is a queuing mechanism, and so in some cases it may take some time. So if you do have a scenario where you need a guaranteed amount of time to copy, it's definitely suggested that you would use a VM somewhere in that Azure region and perform the copy directly to make sure that you get a very consistent time to completion. Parallel block upload. This is just a really simple fix that you can do when you're uploading files. We don't do it by default in the client library because we don't know what device we'll be running on and what else you have going on that device. So we try and be responsible about the amount of resources we'll consume. But if you set up just a couple lines here around the thread count and the default connection limit, this allows one blob to upload much more quickly by using multiple connections. If you're uploading many blobs, upload the blobs in parallel. This goes back to the partition limits we were talking about earlier. In terms of if I'm uploading many blobs, that's sending different requests to different partitions and allowing that scale out effect as opposed to putting all of the traffic against a single partition. So a better way to do this is to do two specific, what we call point queries, two specific queries for a specific entity. This one feels a little bit less efficient because now I'm making two server calls, but each of them now is a single point query instead of a partition scan, so it's much more efficient. Just trying it out on my dev box, no specific optimized environment, anything like that. I didn't even make them in parallel. Just trying this versus the previous slide, consistently performed 5x faster, 5 times better than the previous solution. So let's talk about inserting entities. So if I had 1,000 entities to insert, and you can see my simple entities here, where it's just going to be in a partition key of standard and then just the number 0 through 999 in the row key. This might be one way to insert 1,000 entities. Just loop through the numbers, insert each one of them one at a time. So on my machine, this took 109 seconds to complete. Not bad, but I wanted to do better. So the first thing I do is I turn Naggle off. So Naggle's algorithm is an algorithm that can help in certain network circumstances. It does not help with table storage and queue storage or any very small operations against the storage service. So we generally recommend turning it off. So you can see using Service Point Manager there to turn it off for the table service endpoint. You could also turn it off globally either way, but this kind of narrows it down to just the table endpoint in case you need it on for something else. And then we try exactly the same code as we had before. Now you can see the graphs in terms of the time to complete a number of entity inserts. We've now decreased 109 seconds down to 42. Now let's try making these in parallel. So we've now continued to set Naggle off, but now we're going to do parallel entity inserts, allowing for actually up to 10 entities to be inserted at a time, just using a .NET parallel for each. Nothing fancy here. So now we've dropped from 42 seconds down to 4 seconds by putting this in parallel. Tables support batch transactions. That's the one part of this that isn't necessarily applicable to blobs or queues. But for tables, we can get even better in that we can say do batch operations. So these couple lines of code combined with the for loop now has multiple batch transactions going on. Each of them contains 100 insert operations that can be executed in a single batch. So this now gets us down to 1.7 seconds by making only 10 calls instead of 1,000 calls. And then finally, of course, we can make those batch transactions in parallel. So again, we've used a parallel for each. We've created the batches, only 10 requests. And finally, we've gotten down to about half a second from the original 109 seconds. So about 99.5% faster. And again, just a few lines of code here. So these are definitely things that you should go back to your applications and make sure that you're doing. Naggle, parallelism, and using batch requests. So now security. What we're going to cover in this section is auth methods. We support shared key, shared access signatures, and public, and then encryption methods as well. So in auth methods, we support two that have been around for a very long time. Shared key, which is each account has two shared keys that give you access to everything in the account. They're the admin keys. You can do deletes, you can do writes, you can do create, read, anything on any object in the account can be done with the shared key. Shared key is used to sign requests. You can read in our documentation how all of that works. Then we support public access. So you can configure a blob container to be public read access. And then this is great for web content. All reads will succeed. Writes, deletes, all of that is still shared key only. So for shared access signatures, to talk a little bit about how they work today, the one thing that's worth remembering about shared access signatures is they're computed, not stored. So with shared access signatures, the account owner creates a string that represents the request permissions, saying how long they're good for, what permissions the user is going to get, what objects that they can reference. Then they sign that string with their shared key, send the signature and that string to the user. The user includes those with the request as part of the URL, and then the user tries to make the request. When the server receives that request, it takes that permission string and tries to sign it with the shared key again. If that matches the signature that was provided, then the request is allowed. If not, then the request will be disallowed. Some notes on this, as I said, they're not stored, they're computed. This means you can have as many as you want. There's no limit to the number of SAS tokens you can use, the number of permissions that you can specify. You can store what's called a stored access policy on a blob container. It can be referenced by these SAS tokens. This makes those SAS tokens revocable. It means that you can remove that stored access policy and all of the SAS tokens that referenced it will fail. We have some SAS improvements coming this summer, so this is just to let you know they're on their way, some improvements to it that actually are in response to a lot of user feedback. So a lot of the developers out there have been giving us great feedback on shared access signatures, and so these are a few improvements we have this summer to help address that. The first of these is account SAS. So this has been long requested. It's the ability to create one SAS token that applies to an entire account. The most important capability this gives you is you can create one read-only SAS token for an entire account and really give somebody read-only access to your entire storage account. You don't have to give out the shared keys anymore. In fact, by giving read and write permissions, or read, write, and delete, even your application in the cloud doesn't need to use the shared key anymore. With this, you really can use shared access signatures for everything, and we definitely recommend using them wherever possible. The second one, one of the pitfalls of shared access signature is if it were to be used over HTTP, because anybody who captures that signature can then use it from wherever they are. So we want to make sure that the user using the shared access signature uses it over HTTPS. So now we actually support putting a additional option on the SAS string saying this SAS can only be used over HTTPS, and that will make sure that that token will fail and any applications that we're trying to use it that way can be fixed. And the last one again goes at kind of a similar thread of what if somebody gets the SAS token and wasn't supposed to. This is IP-ACLed SAS or IP-limited SAS. This allows you to put an IP address or an IP address range on the permission string, which makes the shared access signature only usable from that particular IP address. So even if somebody else were to get that, shared access signature, they wouldn't be able to use it unless they were at that IP. Also, during build, we're going to be releasing our client-side encryption preview. So a lot of people have been asking, how do I encrypt my data? So this is our first step at making it much easier to encrypt data stored in Azure Storage. So what we've really been aiming for is getting best practices written into our client libraries, make it really easy to kind of transparently encrypt your data as you're uploading it or decrypt it as you're reading it. Also get really good integration with Azure Key Vault to make sure that key management is as easy as possible. And then also just for client-side encryption, one of the really important things about it is it allows you to maintain control of your keys. So you could use Key Vault or you could use your own key management service. So it's really important to give you the option of where you want to store your keys, how you want to manage them, and we've tried to make sure that you have those options. So one of the advantages to that is the storage service actually never sees the keys that you use. Again, if you choose to use your own keys, maybe on-prem, if you're doing a hybrid cloud scenario, you can encrypt your data on your own premises, upload it to the storage service. The storage service never actually sees the keys that were used. And then additionally, you get flexibility in algorithms. So we've tried to use industry standard best practices, but if you have other needs for compliance or security, then you can use your own algorithm or a different algorithm for the encryption. So when's it coming? As we said, it's actually available now. It's actually ready for you to use over the next month or two. We really want your feedback. What's supported now? We have full blob upload, range or full blob download, tables. You can do property level encryption, so you can actually specify which properties on each entity that you want to use. And then queues, each message is encrypted. We're using what we call envelope encryption. This is, again, an industry best practice. For performance, we generate a symmetric key, encrypt your data with that symmetric key, and also a unique initialization vector for each object, and then encrypt your data with that key. Then we'll encrypt your key with the asymmetric key that you provided, the wrapping method that was specified by the developer. The nice thing about this is the Azure Storage Client Library never actually has access to your key. We just call out to a method that does the wrapping of the symmetric key. Then we store the encrypted symmetric key as metadata on the encrypted object. You don't have to have any additional data store for this. So let's go ahead and look at a code sample for how this will work. So the first thing you're going to do is you're going to create a crypto service provider and an AES key wrapper. This is just what's used to wrap the symmetric keys. You pass in the key. Again, this is all your code. This doesn't use the storage client library yet. The next piece is, as part of the blob options, we're going to need a blob encryption policy. So this says we're going to encrypt the full blob using that wrapper that you already specified. And then set that on the commonly used blob request options. This was where we set parallelism and things like that earlier. So we just set the encryption policy now. And then finally, we just upload the blob. And this all happens transparently. This upload from stream, because it has that options provided, will result in an encrypted blob being uploaded, all the metadata being stored correctly. To download this blob, we can do exactly the same thing on the other end. We use the same options object that we did before, but again, all we have to do is download to stream using that options object, and all the decryption happens transparently. So we hope this makes it much easier for you to encrypt your data. We don't have to have many developers writing their own encryption methods to secure their data. Also, we plan on extending this to our other languages. For example, Java. to make sure that users who are reading and writing using multiple client libraries will actually be able to read the data written with the other client library and not have to implement different encryption methods on their own. How to get started with it? Check out the Azure Storage blog. We've got an introduction, code samples, instructions for how to get started, and then super important, give us feedback. We're in a preview. That preview won't last forever, so it's this limited preview, but it's wide open for you to give us feedback. We really want to make this as great as we can for all your scenarios, so that you can really secure your data seriously. So we have some related content as well for you to go ahead and take a look at after this talk. First is the Azure Storage Performance and Scalability Checklist. This is on azure.com and goes through all the best practices we just talked about and more. Again, very quick fixes, things that you can make changes to your application today and make it perform much faster. We also now have the table design guide that just came out recently and has the table design patterns that we just talked about in terms of hot partitions and query first design, and many, many more that are great for you to include in your applications. And then finally, the Azure Storage blog. Definitely put that in your favorites. Make sure that you're checking that regularly for any announcements, tips and tricks, things like that you can be aware of. Great, thanks very much for watching. I do want to mention a couple other resources. Definitely take a look at the rest of the Azure talks on Channel 9 so that you can get more of a picture of the Azure platform. Also, make sure if you're at Build to tune in to Jason Hogg's talk. He's going to be talking about an overview of storage, but also some new capabilities that we're announcing. So thank you very much for watching. Hopefully this has been very informative for you.